We're going to continue our journey of finding our center. This time, we are going to go to something that has two dimensions. It'll have a base and a height. So instead of just a rod or a meter stick, this will be something like a sheet of plywood. We'll start out with something that's got a pretty basic shape, and that basic shape is that. That's pretty darn basic. So what we will do is talk about the length and the height of this object, and we will calculate its center mass on an x-axis and on a y-axis. All right, and then after this one, we'll just focus on our x's because those are fun, aren't they? So right now, what I'm going to have is this as a graph. So that will be H, however high up it is. This over here is L. So this is the object that is that block of wood. It's H high, it's L long. All right, I should make that a capital H. And again, it's uniform density. So what we're going to do is find its X center of mass, which will be right about there-ish, but we'll end up calculating that, seeing where that comes from. So anyway, this is 0. So the way we'll do it is the same way we did with the meter stick. Remember I said we can cut the meter stick into 100 centimeter sticks? What we're going to do is take this axis and we're going to slice it into differential pieces of mass. So this slice right there, I'm going to call a differential mass. All right, so it has a small amount of mass that if we add them all up, we'll get the mass of the whole entire object. It is also a differential amount of area, meaning if I take this area and add up all of those differential areas, it'll be the the area of the whole entire object. All right, and remember, if it's two-dimensional, it has a density that is represented with a sigma, and that sigma is mass per area. So it's a big M over a big A, the mass whole divided by the area whole, which means if I break this into pieces, it'll have the same as the differential mass divided by the differential area. So if I were to ask you what the differential mass is, you would say that differential mass is the same thing as the sigma times the differential area. Now, any given area is two dimensions, right? It's a base times a height. So this differential area is this thin little sliver's base. So how wide is that infinitely thin little sliver? Not very wide. And so what we will end up calling that is a differential L or an X. Since we're talking about an X center mass, that differential area has two parts, a dx, a differential x, which is its base, times its height, which is the letter h. And that h stays constant. Okay, so we got to make sure only one thing is changing. That h is constant. That differential x is just the thickness of that guy. So if I were to take a dx times h, that's the area of that green line that I have colored in. So our x center mass, again, we will end up calculating the same way we've done before. The x cm is simply 1 over the mass of the whole thing multiplied by the integral from 0 to L, and it will be x dm. All right, same formula we've used before. We do have the same Swapartuna dm because that differential mass is equal to a sigma times a differential area, which means it is equal to a sigma times a differential x times height. So what this will end up being is the integral from 0 to L, and it will be x times this differential mass, which is sigma h dx. All right, that is the integral that we will end up multiplying everything by. Remember, this will be multiplied by 1 over the mass. Now, what I'll end up showing you is how we can simplify that 1 over the mass in terms of a density when we get closer to the end. Now remember, when we integrate this, constants can be fished out. The density of this object is a constant. We can fish it out of the integral. The height of that object stays constant because it's a nice flat horizontal line. So that means sigma and h can get fished out, and this integral ends up looking like sigma h over m multiplied by the integral from 0 to L x dx. So it looks pretty similar to what we've been doing, doesn't it? So this is simply going to be x squared over 2. All right, so this ends up being sigma h over m times x squared over 2, and we will go from 0 to L. So we'll put the L there, we'll put the 0 there. This ends up just becoming sigma h over m L squared over 2. Now remember, this mass is the mass of the whole object, isn't it? And I can simplify that by saying, well, wait a minute. The mass of that object is the same thing as the density of the object times the area of the whole thing. So the mass whole is equal to sigma times the A whole, right? Mass per area, which means mass is equal to density times area. So what I'm going to do with that letter m that is in the denominator is I will replace it with, this is the numerator, the denominator now. Instead of writing an m, I'm going to write sigma times area. Now, that area is the A whole, the area of the whole object. And this whole entire block of wood here has an area that is the whole entire base times the whole entire height. So the base that is the whole object is capital L. The height of the whole object is capital H. So this will be then replaced with those die in H over in L times H, which means those H's die also, don't they? And I'm going to multiply that by what this integral ends up being, which is L squared over 2. And then you put the 0 in and it kills everything, so I'm not going to mess with that. So that L squared kills that L squared, and its center mass is simply L over 2, at least it's x center mass, I should say, sorry. So let me erase that, which means our x center mass is simply L over 2, which you could all tell by looking at that object. Now, the next thing I will do is say, all right, that wasn't too tough. What if I were to ask you about its y center mass, okay? And for that, what I'll do is a very similar thing. I'm just going to change colors and say, well, what if I want to know the y center mass? Then instead of slicing things up along an axis and adding it up, I'm going to slice stuff up on a y-sis and add it up. So now this red sliver corresponds to what that green sliver is. All right, so this is a differential mass, and it is also a differential amount of that area. And my bounds now, instead of going from 0 to L with a constant h, I'm going to go from 0 to h with a constant L. So my y center mass is going to end up being 1 over the mass whole, because that doesn't change whether I'm talking about an x or a y. I'll integrate from 0 to h now, because again, I'm integrating along a y from 0 to h, and this will be a y now instead of an x times a dm. So you see how that formula corresponds to this formula, 1 over m, the integral from 0 to L x dm. All it is 1 over m, the integral 0 to h y dm. The differential mass is the same differential mass. It's a sigma times a differential area. The differential area then is a differential y times an L. So again, it's a differential y, the thickness of this little sliver right there, we're going to call that a differential y, or a differential h, it doesn't matter. It would probably make more sense to call it a differential h or a y. I mean, it doesn't matter. I'll go differential height times the constant length. So that's what I will refer to the differential mass as, times the sigma. So it ends up becoming 1 over the capital M. This is from 0 to h, y times sigma L dh. So it's a differential height and this. And then you see again, it's the same kind of procedure we did before. This sigma and the L are constants, aren't they? So I'm going to fish those out the same way I fished out the sigma and the h before. So it becomes sigma L over M. And then I will integrate from 0 to h y dh. And again, a height and a y are the same thing. So if you want to call that a dy, go right ahead. That would probably make Stelzer a little happier than the way I have it written here. A y dy. Doesn't matter though, they're the same thing. You know, this just becomes y squared over 2. So this again is a sigma L over, now remember that mass, the same swapstitution I did when I found the x center, I can do with the y center. This will be the density times the length times the height. So those two die. And what I'm left with then is just that h in the denominator. This becomes y squared over 2, and I go from 0 to h, and I'll plug that h in there, and this becomes h squared over 2h, doesn't it? And we know that kills that, so this equals h over 2, and that should make sense. There is our y center, half of the height. Our x center is half of the length, and that's how you would find your center if you were a sheet of plywood or something with 2 dimensions like that. Usually they'll just say, hey, give me your x center is all they would ask for. And so we have just continued our journey, 2 dimensions of finding our centers. Namaste, huh? And yay, physics.